Hello, everyone. Welcome to Anand's Academy. And today we're going to take a look at the arithmetic and geometric progression from the series chapter of the 4037 additional mathematics syllabus. So, what does the syllabus statement say? 12.3 states to recognize arithmetic and geometric progressions and understand the difference between them. 12.4 states to use the formulas for the nth term and for the sum of the first n terms to solve problems involving arithmetic or geometric progressions. Some notes and examples include problems may be in context, formulas are given in a list of formulas. Finally, 12.5 states to use the condition for the convergence of a geometric progression and the formula for the sum to infinity of a convergent geometric progression. The notes includes this includes explaining why a particular geometric progression has or does not have a sum to infinity, and formula is given in the list of formulas. Now, let's take a look at the lecture notes. I think you recall the definition of a number sequence or progression from the Maths T syllabus. So, what does it mean? A number sequence is an ordered set of numbers that satisfy a rule. The numbers in the sequence are called the terms of the sequence. In our syllabus for additional mathematics, we will learn two special number progressions. One is the arithmetic progression, shortened for AP, and the other one is geometric progression, short for GP. So, what is an arithmetic progression? An arithmetic progression is a special type of progression where each term differs from the next term or before by a common difference. For example, 2, 4, 6, 8, 10. In this case, each term differs from the next by positive 2. So we add positive 2 to get the next term and we deduct positive 2 to get the previous term. All right. Now let's take a look at some notations involving the arithmetic progression. Here, A means the first term, D is the common difference, L is the last term, and N is the term number. So arithmetic progression can be generalized to be A, the second term to be A plus D, the third term to be A plus 2D, the fourth term to be A plus 3D, and the fifth term to be A plus 4D. From this, we can find a relation between N and A and D. What's the relation? As you can see, for the second term, the coefficient of D is 1. For the third term, the coefficient of D is 2. For the fourth term, the coefficient of D is 3. And for the fifth term, the coefficient of D is 4. So it is N minus 1 times D. So in general, the nth term of an arithmetic progression is given by A plus N minus 1 times D. And that's how we can find the general term or the nth term of an arithmetic progression. It is also wise to know that the nth term of an arithmetic progression is the arithmetic mean of the previous term and the term next to it. So the proof of this is given here. So first we take t of n minus 1, t sub n minus 1 plus t sub n minus n plus 1. We take the average. Then we write our generalized formula, a plus n minus 1 times d. The generalized formula for n minus 1 would be n minus 1 minus 1 because we're taking the n minus 1 term. So n minus 1 is in place of n. So minus 1 that we get n minus 2. So here it is written over here. And for the next term, it is a plus n minus 1 plus 1. Here, here n minus 1 is being added with 1 because we are taking a look at the n plus 1th term. The n plus 1th term is put in place of n, and then the ones get cancelled out, and therefore we get n minus 1 plus 1, which is simply n times d. We distribute the d across n and 2. Then we take 2 common over here. So n plus nd plus nd is simply 2nd, and then minus 2d is just d. We take 2 and d common, so it becomes 2 into n minus 1 times d. And A plus A is simply 2A. So there is a common term that is 2, and this gets cancelled out with the denominator, and we get A plus n minus 1 times D, which is simply the nth term of an arithmetic progression. Therefore, this is equal to the left-hand side, and it is thus proven. Now let's take a look at the sum of an arithmetic progression. So let's consider the series A plus D, A plus 2D, and then L minus 2D, L minus D, and the last term. So first, let's write it in ascending order or descending order if D is negative. Um, so we will first write this starting from A and ending with D. And then we will write this again starting from the last term and ending with A. So there's two ways of writing it. If we add everything on the left-hand side and on the right-hand side, we see a certain pattern. So this gives you A plus L. This also gives you A plus L because A plus D plus L minus D. The D's get cancelled out, and we get A plus L. The same thing happens with this. When these two terms are added together, we get A plus L as well. And for each and every n term, we get n terms, we get A plus L. So there is a total of n A plus L terms. So on the left-hand side, it becomes 2s of n, and on the right-hand side, it becomes n A plus L because there are n terms in this progression, and there are n A plus Ls. So subjecting S of n, we get S of n to be n by 2 A plus L. And this is the famous formula that Carl Friedrich Gauss used in his early days to sum the numbers from 1 to 100 in a matter of minutes or seconds because he was very fast. So this is the sum of n terms of an arithmetic progression. This is very important, and you should know this. But the last term isn't always known. They might give you the number of terms, the common difference, and the first one. So how can we write the sum in terms of those two? We can replace the last term with T of n, A plus n minus 1 times D. So in place of L, we write A plus n minus 1 times D. The two A's get added up to give you 2A, and the n minus 1 times D is just there. So another way of writing the S of n for an arithmetic progression is n by 2, bracket open, 2A plus n minus 1 times D, bracket close. And this is the more conventional formula that we will be using in our problems. Now comes the geometric progression. So what is a geometric progression? It is a special type of progression where each term after the first term is found by multiplying the previous one by a fixed number called the common ratio. An example of this would be the series 2, 4, 8, 16, 32, where each term is multiplied by 2 to get the next term. And the previous term is found by dividing by 2, as follows. So what are the notations involved with geometric progression? Well, A is the first term, R is the common, excuse me, sorry for that. R is the common ratio, and N is the term number. So here are some terms for our generalized geometric series. Like in the arithmetic series, there is the first term. The second term is found by multiplying the common ratio with the first term, AR, it becomes AR. Third term is AR squared. Fourth term is AR cubed. And the fifth term is AR to the 4. So we can find a relation between N and the power of R. So N and the T of N would be simply given by A times R to the N minus 1, because for the fifth term is 4, for the fourth term is 3, for the third term is 2, is N minus 1 of the term number. So T of N is simply given by AR to the N minus 1. Like the arithmetic series, there's also a relation between T of N and the previous term and the next term. And that is found by the geometric mean. So T of N is simply given by the geometric mean of the previous term and the next term. What's the proof of this? So let's choose the right hand side of our equation, this part over here. We have t of n minus 1 and t of n plus 1, where the generalized formula, so t of n minus 1 would be, so t of n is simply a to the n minus 1. So t of n minus 1, instead of n, we write ar to the n minus 1 minus 1. So it becomes a to the n minus 2. For t of n plus 1, we simply, instead of n, we write n plus 1, and then we keep the minus 1. The minus 1 and plus 1 get cancelled out, and it simply becomes ar to the n. Okay, multiplying with these two, we get a squared times r to the n to the 2n minus 2. We can take the second power, t, to be common in our power or in our exponent, and that cancels out with the root. Therefore, we get ar to the n minus 1, which is simply the generalized term of a geometric series, and that is equal to the left-hand side, and it is shown as follows. Now let's take a look at the sum of a geometric progression. Like the arithmetic progression, we will consider a, a, a geometric series. So the geometric series is as follows. The next one is AR, the third one is AR squared, so on and so forth, up until AR to the n minus 1, because that's the general term, G of n. So thus, the sum would be given by A plus AR squared plus dot 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 plus AR to the n minus 3 plus AR to the n minus 2 plus AR to the n minus 1. This is my first, this is my first equation. My second equation, what we are going to do is we're going to multiply each and every term with r. Okay, so multiplying r with each and every term on the left hand side and on the right hand side would give us ar squared plus ar cubed plus dot 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 plus ar n minus 2 plus ar to the n minus 1 plus ar to the n. Okay, there's a slight mistake. I forgot to add plus over here. Okay, now it's fine. All right. Then what we will do is we will subtract equation 1 from equation 2. What's that going to do? Well, take a look. So equation 2 is r s of n, ar squared, ar cubed, dot dot dot, all of this. And then s of n is a plus ar squared plus ar to the n minus 3 plus ar to the n minus 2 plus ar to the n minus 1. All of these terms will get cancelled out. And what we will be left with is simply ar to the n, that's going to be left, and a. So the last term and the first term are the only things that is left in our s of n. Okay, so we take s of n common then, because s of n is present in these two terms, and we get r minus 1 times s of n equals a times r to the n minus a. We take a common and shift the r minus 1 to the right hand side, and we get this expression for our sum of geometric series, which is s of n is equals to a bracket open r to the n minus 1 bracket close all over r minus 1. And this is the formula that we use when r is less than 0 or r is greater than 1. Multiplying the numerator and denominator by minus 1, we get another formula. And that is s of n is equals to a times r 1 minus r to the n over 1 minus r. And this is for r to be in this range. So r is greater than minus 1 and less than 1. A special note for these two formula is that r can never be 1, because that would make it a geometric series. R always has to be not equal to 1. Now let's take a look at the sum to infinity of a geometric series or a convergent geometric series. So let's consider the formula s of n equals to a times 1 minus r to the n over 1 minus r, where r is in this range. As you can see, that this formula is for this range only. So as n approaches infinity, r to the n would approach 0. So how can we verify this? Well, you can take a look into your calculator and then take half. Raise half to the second power. That's 1 over 4. Raise half to the third power. That's 1 over 8. Raise half to the fourth power. That's 1 over 16. Do this up until you reach a very high number, like 50, and this would approximately be equal to 0. Why? Because we can see the fraction approaches 0. So first it was 1 over 8, then it was 1 over, first it was 1 over 4, then it was 1 over 8, then it was 1 over 16, 1 over 32. And this approaches 0. So as n approaches infinity, r would approach 0. Hence, as n approaches infinity, a times 1 minus r to the n over 1 minus r, this would approach a 1 minus 0 because r to the n would be 0 and the new denominator would remain the same. And therefore, our geometric series formula would become a over 1 minus r. Therefore, the sum to infinity is equal to a over 1 minus r, given that r is within this range. Thanks for watching, guys. Please stay tuned for the next video where we will tackle some problems from this chapter.